In this problem, we are going to illustrate how to use Kirchhoff's laws to determine the currents and the voltages across the individual components in a networked circuit. Here's the circuit. It's fairly simple. It has three resistors, R1, R2, and R3. And except for the fact that there is an additional battery E2 here, we could have solved the problem in a very simple manner without really writing down Kirchhoff's laws per se. But because this additional battery exists, we are forced to write down the loop rules and the junction rules applied for this particular circuit. Let's see how that works. The first step in solving this problem is to define clearly what the various quantities that we are seeking. So we are seeking the currents through these three resistors. So I1, I2, and I3 respectively through the three resistors R1, R2, and R3, and that's all we are seeking. We are given the battery voltages E1 and E2. Now, we don't know, this is not a numerical problem, so we don't know what is the directions of the various currents. We could start out any way we would like to, and let's do it this way. We know that there is a total current coming out of the battery E1. Now I'll pretend that this total current is in this direction. Now normally I know that the current goes from the positive terminal to the negative terminal of a battery outside the battery. But the fact that this battery exists here tells me that the current possibly could be in a different way. We don't know that. So let's just put it as the current going in that direction. Now the currents through the resistors also are chosen as per our wish. So we define I1 going in that direction here, I2 as the rest of the I1 going through the R2, and of course I1 and I2 recombine when they reach the other node over here, and then they split again to form the currents I4 and I3. Of course, we'll come to that later, but these two currents have to equal the sum of that two currents. And of course, the combination of I4 and I3 has to equal the current I, which is the same as what left this battery. So in order to set up the equations, we have to identify various loops in this circuit, and there are several of them. There's one loop here, which we'll call as loop 1. There is a big loop which goes all the way on the outside. There's also another little loop on the left side here, and there's also a loop which goes on the outside here but on the inside there. So there are many loops. So let's look at loop 1. So this is our loop 1, and we'll rewrite it here on the left side. So that's loop 1 reproduced there again. It has just two elements, the resistor and the battery, and we can readily write down the voltage balance equation. So as we go from there to there, we gain a voltage E2, and then as we go from there to there across the resistor, we lose the potential drop I3 R3. The sum of that has to be equal to 0. Now you can ask, what about I4? There is a current there left over from our original picture here, but that I4 doesn't really go through any resistor, so at least in this part of the circuit, so we do not count it. So this equation readily gives us the current I3 since we know both the quantities on the right hand side. Now let's look at the another possible loop. So this is shown in red here. So we've separated the circuit into red and white. So let's rewrite this loop 2 in red, and there it is. And now we have the current I, of course, and I2 and the two batteries. So how would the loop equation look like? So if we go from there to there, so I'm gaining a potential E1. The I4 again doesn't do anything. I'm gaining another potential E2, and when I come here, I define my I2 going in the opposite direction to which I'm traveling. So normally I would write this as minus I2R2 if there was a voltage drop, if I was going in the same direction as the current, but my current is now opposite, so I have to write this as plus I2 times R2. So the sum of all three, of course, is 0. So that readily gives us the current I2 in terms of known quantities. Similarly, if instead of taking the R2 in the outer loop, so if we kept the rest of the circuit the same, loop the same, but then came down like this and took R1, we would have another loop, and the corresponding loop equation for that would be E1 plus E2, the same thing, but we would have I1 R1, so which is written over there, and that readily gives us the current I1 in terms of known quantities again. Now there are also other loops. For example, let's consider this loop, and you can write down immediately what the loop equation is. It's just I1 R1 plus I2 R2 equals 0. So that doesn't really, I1 R1 rather plus I2 minus I2 R2 equals 0, but that doesn't give us anything new because we have that here. I2 times R2 equals negative E1 plus E2. I1 plus R1 equals negative E1 plus E2. So we know that those two quantities are equal anyway. So let's proceed to the next step. The next step is to select the nodes and figure out what the currents are doing at the nodes. We could select this node to begin with, and that's simple. I equals I1 plus I2, so that's one equation. We found both I1 and I2. We'll come back to that. At this node, we have I plus I4. Both of them are leaving the node, equals I3 entering the node, and the two equations combined, they both have the i's, and you can subtract the two equations after rearranging and write I4, which is here on the left hand side, in terms of I3 and the I substituted from that equation. So there it is, and so now we know I4. So in the previous slides we derived the expressions for the currents I1, I2, and I3. So let's reproduce that. So there's I3, I1, and I2, and now we know what I4 is. So we've determined, therefore, all the four currents that we wanted to. Now, there are more nodes again, and one could write the equation at this node, for example, and you'll see immediately that this does not give us anything new because it's the same equation as this one, which we determined by combining the two equations at these two nodes. So there is redundancy in the problem, and one just has to ignore it